We've taken a first look at moments now, in particular the first moment being the expectation of the absolute value of a random variable. Let's look at second moments in this lecture. That leads us to L2, the space of square integrable random variables. Consider any measure space. The set L2 of that measure space consists of all real-valued measurable functions for which the integral of the square is finite. Now, as usual, we're playing a little fast and loose here. The elements of L2, like in L1, are really going to be identified as equivalence classes of functions, where we identify two functions if they agree almost everywhere. The first thing we noted about L1 was that due to the linearity of the integral, L1 is a vector space. Well, the same is going to be true with L2, although it takes a little more work to see why it's closed under the vector operations. And here is a key point. Take any two functions, in fact this is just a point-wise statement. Take any two numbers, f and g, then the square of the difference of their absolute values is equal to, expanding it out, f squared minus 2 times the absolute value of fg plus g squared. Now that is the square of a real number, and so it is non-negative. Rearranging that, solving for the absolute value of fg, we find that the absolute value of fg is less than or equal to 1/2 of f squared plus g squared. What we can conclude from that by the monotonicity property of the integral is that if I have two functions, f and g, in L2, then the integral of the product in absolute value is less than or equal to the integral of 1/2 the sum of squares. But using the linearity of the integral, that's equal to 1/2 the integral of f squared plus 1/2 the integral of g squared. And since f and g are in L2, that is finite. So we have this proposition that if f and g are in L2, then the product, f times g, is in L1. That's exactly what this says. And a corollary to that is that if you have a finite measure, like a probability measure, then L2 is actually a subset of L1. And the reason for that is that in a finite measure space, we can take the function g equals 1. That function will be in L2 and L1 and LP, if you remember what that is. That's just because the integral of 1 squared d mu is equal to the integral of 1, which is the measure of the entire set, which we're assuming is finite. And therefore, if f is any L2 function, from the proposition above, we get that f times 1 is in L1. And so any L2 function is actually in L1. Now, following very similar calculations, we could right away deduce that the sum of two L2 functions is back in L2, but I'm going to do that in a systematic way that uses a named inequality, which you will use over and over as we proceed through this material. It's called the Cauchy-Schwarz inequality. Let's introduce a little bit of notation first. Given some functions in L2, we'll write the L2 norm to be the integral of the square rooted. I'm calling it a norm. The fact that it's a norm is going to be a proposition on the next slide. Similarly, we'll write the L2 inner product between f and g to be the integral of the product. And so far, what we know is that these are finite numbers whenever f and g are in L2 by the propositions on the previous page, and in fact by the definition of L2. Here is a key soft analysis inequality, the Cauchy-Schwarz inequality. It says that if f and g are any two L2 functions, then the absolute value of their inner product, which is less than or equal to the integral of the absolute value of the product of the functions, is less than or equal to the product of their L2 norms. Let's prove this. So for the first inequality, this is just the statement that the absolute value of the integral is less than or equal to the integral of the absolute value, which we know holds in general for Lebesgue measurable functions. So it's the second inequality that actually takes work. In order to prove that, we use the following really nice trick. For any real number t, we can define a function p of t to be the integral of absolute value of f minus t times absolute value of g squared. Now, at the moment, we haven't shown that L2 is closed under linear combinations. This might not be an L1 function a priori. We're going to see that it is, but that doesn't matter. For now, let's just note that this is the integral of a non-negative measurable function, and so is a non-negative number for any t. Could be infinite, but it's a non-negative number. Now, let's expand out inside, and we'll see that we have f squared minus 2t times the absolute value of fg plus t squared times g squared d mu. And now we see that this actually is a finite number for every t, because as we've shown, each of these three terms is in L1 when f and g are in L2. And therefore we can use the linearity of the integral to write this as the integral of f squared d mu minus 2 times the integral of absolute value of fg d mu times t plus the integral of g squared d mu times t squared. And writing those terms in terms of the quantities up here, this is the L2 norm of f squared minus 2 times the integral of absolute value of fg d mu times t plus the L2 norm of g squared times t squared. Now, I've called this function of t p of t because it's a polynomial. It is a quadratic polynomial. And what we have shown is that this quadratic polynomial takes non-negative values on the entire real line. What does that mean? That means that this is not allowed. This polynomial cannot have two distinct real roots. It could have a double root somewhere, or it could have no real roots. But if it has two distinct real roots, it will not be positive everywhere. Well, we know from the quadratic formula how to decide when that happens. The fact that this is a non-negative quadratic polynomial tells us that the discriminant of this quadratic is non-positive. The discriminant is b squared minus 4ac. And that has to be less than or equal to 0. Well, if you expand that out, divide through by 4, and take square roots, what you're left with is the Cauchy-Schwarz inequality. Now, a nice corollary to that is that L2 is actually a vector space, and the L2 norm is genuinely a norm. Let me note that I've written the relationship between the norm and the inner product here. That is to say, squaring both sides, the assertion is simply that the L2 norm squared, which is the integral of f squared d mu, is the same thing as the inner product of f with f, which is the integral of f times f d mu. That's of course true. This is the relationship we would like to have between a norm and an inner product in an inner product space. And so in fact the statement here is going to be that L2 is an inner product space. So why is it an inner product space? Why is it a vector space? Well, let's first check the vector space operations hold. If I have any constant in the reals and any L2 function, I just need to check that alpha times f is an L2 function, which is the same thing as checking that the L2 norm of alpha f is finite. Let's square both sides. That's equal to the integral of alpha f squared d mu. And of course, we know we can pull out that constant. That's alpha squared times the integral of f squared d mu, which is alpha squared times the L2 norm of f squared. And taking square roots, we see that the L2 norm of alpha f is the absolute value of alpha times the L2 norm of f. That's one of the prerequisites for being a norm, verified right there. Now, if f and g are in L2, if I try to take the L2 norm squared of their sum, I just need to show that that's finite. So that's equal to the integral of f plus g squared d mu. And if I FOIL out the inside, that's the integral of f squared plus 2fg plus g squared d mu. We know that fg is in L1 and f squared and g squared are in L1, and so all the terms are integrable. We can therefore use linearity of the integral to write this as the integral of f squared plus 2 times the integral of fg plus the integral of g squared. And now, by the Cauchy-Schwarz inequality, that middle term is less than or equal to 2 times the L2 norm of f times the L2 norm of g. But those outer terms are the L2 norm of f squared and the L2 norm of g squared. And so that is the L2 norm of f plus the L2 norm of g squared. Taking square roots, that shows that the L2 norm of f plus g is less than or equal to the L2 norm of f plus the L2 norm of g, which both verifies that f plus g is in L2 and that the L2 norm satisfies the subadditive property of norms. So the only thing we have left to check, now that we know that L2 is a vector space, is that the L2 norm is genuinely a norm. And the only condition left on that score is to see what happens when it equals 0. If the L2 norm of an L2 function equals 0, then squaring both sides, that says that the integral of f squared d mu equals 0. Now, f squared is a non-negative function, and we know that if you integrate a non-negative function and get 0, that function must be 0 almost surely with respect to the measure, which is the same as saying that f is 0 almost surely with respect to the measure. And here we see again, it's important that we are not actually working with functions, but with equivalence classes of functions defined up to a set of measure 0. Otherwise, just like L1, the L2 norm would not be a real norm, it would be a semi-norm. So L2 is a normed space. In fact, it is an inner product space. And even better, it is a complete inner product space, which is called a Hilbert space. That means that it's an inner product space and that the norm induced by the inner product gives a Cauchy complete metric structure. In other words, if I take any sequence of L2 functions that is a Cauchy sequence in the L2 norm, then it converges to a unique limit that is in L2. By the way, this completeness property also holds for L1 and even for the general LP spaces that we've mentioned briefly. We're not going to prove this right now. We will soon, and it will actually have very important probabilistic consequences, particularly in the L2 case. But speaking of probabilistic consequences, the most important developments that we get from L2 are the notion of covariance and correlation. Now we're working in a probability space, and remember, we showed that means that L2 is contained in L1. In other words, if you have a finite second moment, then you have a finite first moment. Well, let's look at that first moment, which is the same thing as the L1 norm of a random variable x, which is the same as the integral of its absolute value. I could cleverly write that as the integral of the absolute value of x times 1. And now I will use the Cauchy-Schwarz inequality to conclude that that is less than or equal to the L2 norm of x times the L2 norm of 1. But the L2 norm of 1 is the integral of 1 squared dp, which is the probability of the whole sample space, which is 1 because this is a probability measure. And so we have this nice inequality, that the L1 norm is less than or equal to the L2 norm in a probability space. In probabilistic language, we could write that as the absolute value of the expectation of a random variable, which we know is less than or equal to the expectation of the absolute value, is less than or equal to the square root of the second moment. Now, since the expected value is finite, we can modify our L2 random variable by subtracting it off, which is something we will often do. Given any two L2 random variables, or in fact any L1 random variables, we can center them. X circle is x minus its expected value, and y circle is y minus its expected value. We call these random variables the centered versions of x and y. Centered is another way of saying that they have expectation 0, because notice that the expectation of x circle is the expectation of x minus the expectation of x. And by the linearity of expectation, when all these terms are finite, that's the expectation of x minus the expectation of x, which is indeed 0. Now, L2 is an inner product space, and so we could take the inner product of our L2 random variables. But it turns out in probability, it makes more sense to take the inner product of the centered versions of the random variables. And that's how we define covariance. The covariance of two random variables is the expected value of the product of their centered versions, which is the same thing as the L2 inner product of their centered versions. Now let me write this out a couple of ways. By definition, this just means the expected value of x minus its expected value times y minus its expected value. But we can FOIL out the inside, and that will give us xy minus x times the expected value of y minus expected value of x times y plus the expected value of x times the expected value of y. And if I now use linearity of expectation and pass it through these four terms, notice that here we will get the expectation of x times the expectation of y. Same here. And of course, same here. So we get these three terms will be the same up to sign, 2 with a negative sign and 1 with a positive sign. And so this reduces to the expected value of x times y minus the expected value of x times the expected value of y. That is another, often more convenient way to write the covariance of two random variables. We can also define variance. The variance of a random variable is just the covariance of it with itself, which is the same thing as the expected value of the square of its centered version. And following exactly the same calculation we did above, setting x equal to y, that gives us the expected value of x squared minus the expected value of x, quantity squared. And by what we did on the previous slide, we know that that is non-negative. The covariance could take a positive or a negative sign, but the variance of a random variable, the diagonal covariance, is always non-negative. Why would we care about these quantities? I hope to start convincing you in the next few slides that they are meaningful. For example, here is a basic lemma. If x is any L2 random variable that has variance 0, then it is actually constant. Again, because our random variables are only defined up to a set of measure 0, it is constant almost surely. Now that's really just a restatement of a theorem we've already proved, because what we're saying here is that 0 is the variance of x, which is the expected value of the centered version of x squared. But that centered version of x squared is, of course, a non-negative random variable. So we know that if the integral of a non-negative random variable is 0, then that random variable is 0 almost surely, which of course implies that x circle is 0 almost surely, but x circle is x minus its expected value. And so that says that x is equal to its expected value on a set of full probability. Its expected value is a constant, and that proves the result. Let's do a few calculations. These will be useful calculations to have under our belt, but they also serve to emphasize the fact that the variance, just like the expectation of a random variable, is a function of its distribution alone. Let's take a Gaussian normal random variable with parameters alpha and t. We showed in the last lecture that we could write that alternatively as this affine transformation of a standard Gaussian with parameters 0 and 1. And we also showed that 0 in that case, or alpha over here, is the expected value of such a random variable. But we have yet to identify what the parameter t means. Well, the variance of x is the expected value of the square of its centered version. And since its mean is alpha, it's the expected value of x minus alpha squared. But since x and this affine transformation of z have the same distribution, we can substitute this in for x and get the same answer under the expectation thanks to the change of variables formula. Thus, subtracting off alpha from that affine transformation, this is the expected value of root tz squared. And using the linearity of the expectation, this is t times the expected value of z squared. And last time we computed that the expected value of z squared was equal to 1. And so we see that the parameter t in a general normal random variable is its variance. How about some of the others that we computed last time? Let's let capital T be an exponential random variable with parameter alpha. We computed that its expected value is then 1 over alpha. Well, its variance is going to be the expected value of t minus 1 over alpha squared. And now we'll just use the change of variables theorem directly to write this as the integral over the positive real line of little t minus 1 over alpha squared times the density, alpha e to the minus alpha t dt. And I'll spare you the Math 20b calculations, but at the end of the integration by parts, you'll get 1 over alpha squared. So the variance of an exponential random variable is the square of its mean. How about a Poisson random variable? We calculated that a Poisson of parameter alpha has expected value alpha. The variance of this discrete random variable, again, this is the expected value of the square of the centered version. That expected value, being an integral of a pure point measure, reduces to a sum, k going from 0 to infinity, of k minus alpha squared e to the minus alpha to the k over k factorial. And again, you can expand this out and do it much the way we did last time by cleverly identifying these things as appropriate derivatives with respect to alpha, or you can rearrange the sums combinatorially. Either way, at the end of the day, you're going to get alpha. The variance of a Poisson random variable is the same as the mean. Calculations like these are the bread and butter of undergraduate probability classes. I'll leave it to you to do any further calculations of variances of particular distributions. But what about covariances? Those are determined by two random variables. The most important thing we can use covariances for is to see when they're 0. We say that two L2 random variables are uncorrelated if their covariance is 0. Now, covariance, remember, is an inner product. It's an inner product of the centered random variables. So uncorrelated random variables are those whose centered versions are orthogonal in L2. That's a geometric sounding quantity. We'd like to understand what it means probabilistically, and we will head in that direction shortly. Let me note that in general, there is a normalized version of covariance called correlation. The correlation coefficient of two random variables is the covariance divided by the square root of the product of the variances. And we could rewrite that instead as the expected value of the centered versions product divided by the L2 norm of the centered versions product. And by the way, that L2 norm, that is the square root of the variance, also has a name. It is called standard deviation. Now, one reason to write correlation instead of covariance is that by the Cauchy-Schwarz inequality, the correlation's absolute value is less than or equal to 1. So this gives some kind of measure of how related the two random variables are on a scale from -1 to 1. Now here is a key consequence of uncorrelation. If random variables are uncorrelated, then their variances sum. To be more precise, the covariance doesn't care about adding a constant, like this. And if I have a sequence of pairwise uncorrelated random variables, the variance of the sum is the sum of the variances, which is kind of a surprising result given that variance is a quadratic function, not a linear function. So to see why this is true for the first property, just note that the centered version of x plus alpha is the same as the centered version of x, since both of them have expected value 0. And so that takes care of this statement immediately. For the second statement, we just multiply everything out. The variance of the sum, which is the expected value of the centered version of the sum, squared. Well, the centered version of a sum is the sum of the centered versions because of the linearity of expectation. And now I'll write that square as the sum over j of xj centered times the sum over k of xk centered. And using linearity, I'll pull that double sum outside the expectation. In other words, this is the sum over two indices, j and k, of the covariance of xj with xk. Our assumption is that these random variables are uncorrelated, meaning that for j not equal to k, this is 0. And so that becomes just a single sum, j going from 1 up to n, of the covariance of xj with itself, which is the definition of the variance of xj, proving the result. This additivity of variance under uncorrelated random variables will play a key role in a big theorem we will prove next time, the weak law of large numbers, which will go a long way to promoting our understanding of what expected value actually means. But before we go there, let's make one more attempt to understand what uncorrelated really means through a couple of examples. For starters, let's take two events in our probability space, A and B. We know that we can convert them into random variables by taking the indicator functions of those events. And by the way, what kind of distribution does such a random variable have? Well, if I take one of those, I'll call it x. It takes only two possible values, 1 and 0. The probability that it is equal to 1 is the probability of the set A, where it equals 1. The probability where it equals 0 is the probability of the set where it equals 0, which is A complement, which is 1 minus the probability of A. Such a random variable, which takes values 0 and 1 with some probability p and 1 minus p, is called a Bernoulli random variable. So indicator functions are Bernoulli random variables. So if I take any two Bernoulli random variables like this, their covariance is by definition the expected value of the product minus the product of the expected values, but we know that the product of two indicator functions is the indicator function of their intersection. And now we can write this in terms of the probabilities of those events. This is the probability of A intersect B minus the probability of A times the probability of B. That's the covariance of two Bernoulli random variables. And you should recognize that this being 0 is the same thing as saying that A and B are independent events. We will get to independence relatively soon, but you've certainly seen what independence of events means. It means that the probability of their intersection is the product of their probabilities. For another example that is not actually unrelated, consider tossing a fair coin n times. and consider the random variables which measure whether you get heads or tails. xj is 1 if the jth toss is heads, and 0 if the jth toss is tails. We can model this situation with a finite probability space, omega consisting of all sequences of zeros and ones of length n. So this is a finite set with 2 to the n outcomes. We may as well take all subsets in the sigma field, and the probability measure we'll use is the discrete uniform probability measure, which assigns equal probabilities to all outcomes. That is, the probability of any event will be the number of outcomes in that event divided by the total number of outcomes, which is 2 to the n. In this model, xj of an outcome omega, which is a sequence, is just omega j, the jth term in that sequence. And it is a good exercise for you to work out from first principles that in this model, the covariance of xj and xk is either 0 or 1. It is 1 if xj equals xk, so each of these has variance 1, and it is 0 if j and k are different. So two different coin tosses are uncorrelated. That again should tell you something about the relationship between uncorrelated random variables and independence. But don't conflate the two. They don't mean exactly the same thing, as we'll see soon.